Yeah, I think I definitely understand what the problem is, Hans, and really where you're coming from here. So let's see. Yeah, let us see, because you can see, I have the clothes right here. I am the model, and I have many of the clothes in the box, and pretty much it is it. This is it. I'm fitting many clothes in one box, and I need you to solve the problem here. This is cannot go on any longer, and this is ridiculous. Or Hans, really it's not that ridiculous, and it's just a maximum value problem, and we just need to solve it. This is like all of a sudden it is like we like what are we French? We are going to solve the problem. I am just a model, and I just need to do my job. This is so important to me. This is important to the world, and this is important to the United Nations. This is a nation thing. So many nations depend on the style of. Look at this. This tag is like you don't even know who this is yet, right? You do not know who that is, that brand. Okay, so I really need you to solve the problem. Okay, yeah, I'm totally with you there. And so that's what I'm basically going to do here is just try to solve that max problem for you. Okay, so that's what I'm going to do, Hans. And you're just going to sit here, and I guess you're just, okay, yeah, all right, you're trying on clothes now. Okay, great. Well, thanks for joining me, guys, for this video about modeling and really working with functions from formulas and graphs and descriptions, as you can see here. And we're going to solve a max value problem. And so we're going to start with a little bit of review. And wait, I have a problem here, and I am the model, and you are trying to review something. I don't understand. We don't have time for this. Review, what is this? Where are we reviewing? What are we viewing again? Again and again and again, we view the same problem. Hans, do you like zippers? Zippers? Yeah. Oh, I love the zippers. Have you ever been to www.zipit.com? Oh, I see where you're going with this. Perfect. Pause me now and take a few minutes to solve these formulas for the variables that are given. So it gives you a formula. Check this out. This is a triangle. This is do you know what this is? How about this formula? I have 4 formulas. You should be familiar with these. These are expected that we would know these, but we'll get more familiar working with them. So solve for H, R, then T, and I'll pop up the answers in just a moment. Pause now. Alrighty, here are the solutions. Solve for H, R, and T. And I just added there at the bottom that simple interest is what that last formula is, and the rate is always in a decimal form. T is time. So those are just practicing manipulating formulas so that we could solve for variables whenever we want. Speaking of, I have just a few thoughts on algebraic models before we solve that problem we were presented with. So, algebraic models. One of the goals is to create a function that we can solve that has one variable. So the challenge sometimes is identifying what that variable is and using a variety of formulas to express all quantities only in one variable. But formulas can be helpful, so what we can do is we could take the relationships that variables have in formulas and manipulate them so that we can express one variable in terms of another variable. We've sort of experienced this already. We're used to things like y equals something something x, and we recently saw equations that were implicitly defined. So what we're kind of seeing here is that there could be an implicit relationship, and we want to move from implicit to explicit. So, just like you did in the review, you solve for one variable in terms of another, and we got an equation that we could use, that we can plug some values in and solve for that variable. All right, so we're going from an implicit to an explicit, and you'll see what I mean as we solve Hans's problem. So let's get to it. Oh, this is like, oh my gosh, it's been so much time since you have been working on the problem. I am so, finally, I can actually rest a little bit from looking at myself in the mirror. Okay. Okay, well, so the problem is this. We have an 8-inch by 15-inch piece of cardboard to make an open top clothing box. I know, Hans is going to be really upset that we're not using centimeters. Yikes. Okay, here's the deal. A square of side x. Why do we cut out a square of side x? Well, because if we don't do that, then the box will be all misshapen and it won't actually fit together. So there's a top of this box that goes over it. It happens to be the same exact size. You know those clothing boxes that are kind of like gift boxes? So, Hans needs to get his clothes in there. So we cut that out of each corner. Our goal is to maximize the volume of the box. We can do it. So as I draw a picture here of this 15 by 8 box, I just want to tell you that whenever we do problems like this, modeling problems, the solution doesn't come to your mind right away, okay? And so what you got to do is you just got to mess around a little bit to see what you can figure out based on the context of the problem. So we start with a picture. And at this point, I don't really know exactly where it's going, but I just know that we're cutting out these squares out of the corner of the box. So we started with something that was 15. So this goes all the way over there. This is the length of the cardboard. 15 by 8. And the other thing that the problem situation told us, which we wouldn't necessarily know if we hadn't chatted with Hans a little bit and figured out how to actually make a box, is that each little square is, we're going to call that side x. So this one example is the very one that I'm sharing in this modeling section. So it'd be great to just jot down a sketch, and there's some space that you could use in your booklets or in your notebook. But I want to give you that visual again to bring you back to the original context. Here is that open top box, and there's a shirt and a pair of shorts or pants that are in the box as well. And just because a box is made of the same material doesn't mean it has the same amount of volume. Think about if you squeeze this left and right, it would get taller, or if you made it skinnier, it would if you stretch it out right and left, then it would get skinnier, right? So there's a variety of different volumes, and we're going to see a graph later on that's going to be pretty nifty. So we're going to need our calculators for that. All right, so here's the picture, and I'm going to modify this a little bit because we're just going to cut out those corners. We don't need it anymore, so I'm going to sketch a new picture. So here's a new picture, and I'll just do some dotted lines. The dotted lines is where you're going to actually fold up the sides, and you could create an open top box. Now, question, what is the volume? Volume is 3 dimensions, and we multiply those 3 dimensions together. It is volume equals, say it together, length times width times height. And what is the length? What is the width? What is the height? All right, jot this down. The length is 15 minus 2x. The original length is 15, and we subtracted 2 x's off of it. What is the width? It is 8 minus 2x. Why is this the case? Because when we fold up the sides, this length inside here, this dotted line, is 15 minus 2x. And so that side is 8 minus 2x right there. Alrighty? And then the final one, this is not as obvious as you might think, but the height is simply, if you fold up those sides, that little length there is x. So we're letting that length vary so that we can come up with all of the possibilities for the volume of a box based on what we're doing here. So the height is x. How are we doing? Hans, how are we doing? This is like so mathematical, crazy, magical. Okay, I'm like, so my heart is beating with numbers, and I can see numbers flowing off of my heart into the world like bubbles. It is so magical. Oh, thanks. Yeah, that's awesome. So what we'll do now is just write the volume of the box, the volume is, well, length times width times height. 15 minus 2x times 8 minus 2x times x. So I just want to point out here that just a moment ago we had three variables that were describing volume, and now here we just have one variable. And because we now only have one variable, we could use that to analyze the function, and we could go to our grapher. So pull out your calculators. I want you to turn them on and go to y equals . And I want you to simply type that into your calculator as y1 and don't hit graph yet, right? We want to change our window before we actually do that. So take a moment. Could probably pause the video. All right, so you got that entered into y equals. Before you hit graph, don't hit zoom 6 because these numbers are a little bit bigger than normal. I want you to think about this. The domain of this function, what's the smallest x value? What's the largest x value? Well, the smallest x value is actually 0. We're not gonna cut out anything less than 0. You can't cut out a negative value out of the box. Think about the largest value that you could cut out. That one side there is only 8 inches long. So if you cut out more than 4 inches, then you won't actually have something to work with as far as the sides of the box go. You'll have a non-existent side. So the most that the x value can be is 4, and we'll just say that it's inclusive of that so that we can put that in our window. And so that's what I want you to do as your x-min. So I want you to press window, put that as your x-min, and this is your x-max. And then the other piece that we want so that we can actually see the curve is the range. And this is where you have to kind of play with the numbers a little bit. Maybe you could plug in 2 into this equation here, and you could see that it's 15 minus 4, which is 11, and then 8 minus 4, which is 4. So far that's 11 times 4, which is 44, times 2, which is 88. So we're looking at like something kind of less than 100. So what I want you to do is put in your y-min as 0 and go up to 100. So your range is 0 to 100. So that's your window. Change that. Okay, so you change your window and you hit graph. Okay, awesome. You should get something that looks like this. Now I want you to notice right away that this is not, definitely not, a parabola. It kind of looks like it, but it's a little bit misshapen and it's skewed because of the rectangular nature of the actual original piece of cardboard. So the max value happens right here. And what is that value? Well, let's hit second trace or second calc, that's the second piece of it, and then find out what that actual max value is. So we're hitting second trace and we're going to find the maximum. Once you hit maximum, it's going to ask you for a left, the left point. And so you're going to arrow left a little bit to the left. So you're going to arrow left on the curve to the left of that max. Then press enter, arrow right, press enter, and then you're going to guess what that max is. You go towards that point and hit enter. So do that, pause me. You're just telling your calculator, first of all, that you are smarter than it, and you're telling it which max you want to locate, because there actually is another value on this function that will give you some sort of max, but it's a negative value and we don't want it. Alright, so what you'll end up finding out is that the maximum value is, it's the y value, the maximum value is 90.74. So what's the maximum value? 90.74. When, at what height is the height that's going to yield that maximum? Well, that height is 1.67 or 1.6666666, 5/3. Yeah? when you look at that point, you'll see that that point is 5/3, 90.74. But what we were really interested in is what's that max volume, and what does that point really mean? It means 1.67 is what we're cutting out of the box. So that's it. There's much more that we could do in modeling, and there's much more in your textbook that you could look at that's really interesting. It talks about visuals, it talks about using the empirical process of working with units, and then it also gets into some regression that we're going to get into later on in the next unit. All right? So that is just one of the most famous examples about maximum volume, and we just got to check in with Hans here and see if it's going to satisfy this deal here. Hans, 90.74. What do you think? I am the model, and you know I cannot even take in these numbers right now, and you know I don't know why you are restricting me to a box to begin with, okay? Because it is like everybody's trying to put me in the box, and here I am I'm just trying to put my clothes in the box and just do my job, you know, and just try to be the most amazing person in the world. So I don't even know if I can accept your 90.74, but I do like 5/3. That is a very nice number. I like the fractions. So thank you very much, everybody. It is very wonderful to have you take care of my problems.